Hello and good morning to everyone. So our today's lead code question is 3093, which is longest common suffix queries. So basically in this question we are given two arrays named as word container and word query. So in this word container we are given various strings, uh, and in word query we are also given various query strings, right? And for each words query of I, for each string in the words query, what we need to do is we need to find a string. We need to find a string from word container such that the query has the longest common suffix with, right, such that this string, the string from the word containers, has the longest common suffix with the word query of I, or the string from the word query. Now the thing is that if there are two or more strings two or more strings in the word container array that has the same longest common suffix, then we what we need to do is we need to take the string whose length is smaller, right? Which so if if there are two strings in word container and such that they share the longest common suffix, same longest common suffix, then we need to take the string whose length is smaller. Now it may be possible that they have the same length. If they have the same length, then we have to take the one which is appearing earlier in the word container, or whose index is lesser, right? So first we need to find for any query string, we need to find a string in word container which has the longest common suffix. Then the second thing is, if multiple strings are there such that they have the same longest common suffix, then we have to take the one with the smaller length, with the smaller length. Now if they have the same length, then we have to take the one which has smaller index, right? So this is what we need to do. And then at the end what we need to do is we need to return an array of integer named as answer, where answer of I stores the index of the string in the word container array which shares the longest common suffix with the query array, right? So basically for each query we need to store the index of the longest common suffix string, right? And we need to return the answer. So let's see an example to get the question more clearly. So we have taken this example a b c d b c d x b c d. So these are the words and the queries are c d b c d and x y z. So if you see, this is our first query cd. So if you see the suffix, so this also has suffix cd, this also has suffix cd, this also has suffix cd. So all three strings has a suffix of length 2. Now next thing, we need to take the smaller length string. So bcd length is 3 and the rest of the two strings has length 4. So 3 is lesser than 4, so we take this string. So index of this string is 1. So we have stored our answer as 1, right? Then the next query string is bcd. Again all three shares the same thing, right? All three shares the same suffix bcd. So again we take the one with the lesser length. So again we stored 1. Now we have xyz. So if you see, none of them shares any suffix. So none of them shares any suffix, right? So again we need to take the one with the lesser length out of all. So bcd has the lesser length, so again the index is 1. So our output is 1 comma 1 comma 1, right, for this example. So let's see the constraints. So the number of strings in the word container and number of strings in the query can be up to 10 ki power 4, right? So we can have 10 ki power 4 strings in word container and 10 ki power 4 string word query. And each string in word container can have a length of 5 into 10 ki power 3, right? Similarly, each string in the query can have a length of 5 into 10 ki power 3. And all the strings in word container and query both are consist in lowercase English letters only. And now the sum of sum of the lengths of the string in the word container can be at most 5 into 10 k power 5, right? So sum of all the characters from all the strings in the word container can be at most 5 into 10 k power 5, right? Similarly, sum of words from the query length can also be up to 5 into 10 k power 5, right? So let's move to the approach part. So now if you see, what is the problem asking us to do? So the problem is asking us to find the longest common suffix between every query string and container string. So basically what we need to do is we need to do string matching, right? We need to do string matching. And as we know, for string matching, the best thing we can do is use a trie data structure, right? So but there is one problem here. As we know, trie is good for prefix matching, but here what we need suffix. But trie is good for prefix matching. So what we need to do is we need to convert our suffix problem into prefix problem. So if we reverse the strings, then our suffix problem will be converted to prefix problem, and then we can use trie, right? So this is the first thing that we do, that we reverse all the strings and then we'll use trie, right? So suppose if two strings they shares a common suffix, they shares a common suffix, and when we reverse them, their prefix will also be similar, right? Same, they will also share common prefix. So if we see an example, we have abcd and we have xbcd. So if we see, the suffix here is bcd, here also bcd. So when we reverse them, they again shares dcb as the common prefix. So the goal of showing this example is that on reversing, earlier they have common suffix, then after reversing still they have the common prefix of the same length, right? So what we do is we reverse all the container strings and all the query words, and then we use trie. So on reversing, still the problem will be same only. Just what we need to do is, instead of finding suffix, we will find longest common prefix right? Next thing, what our trie structure. So our trie node will contain an array named a child whose size is 26. So it will store, it will store the index of the next nodes. So this array will store the index of the next nodes, and there is one more variable named as index. So what it will store, the best index for the current suffix or prefix that we have traversed now, right till now, right? So this will store the best index for the current suffix or current prefix. So our trie node structure has two things: a child array which will store the index of the next node, and a variable named as index which will store the best index for this current prefix or current suffix, right? And this best index is chosen based on our conditions. That is, we take the smallest length string, and if still there is a tie in the length, then we choose the one which is occurring earlier in the answer, or we can say whose index is smaller, right? So based on these two criterias, we are choosing the best index for the node, right? Now you may think, why we are storing the best index at every node? What is the need of it? So when we traverse during a query, then it may be possible that we stop at some node in the middle of a string, right? So this current node this current node will represent the longest prefix that we have matched or longest suffix that we have matched, right? So now among all the words that shares this prefix or suffix, we need to find the best candidate. So now instead of going to each word and checking which is the best word, we will be storing the index. So this index will tell us that which word is the best among all the words that shares this suffix or this prefix. So now instead of checking all the words, we directly take this index as our answer, right? So that's why we are storing the best index at every node, right? And to update the best index, to update our best index at every node, we have this function. So what this update function will do is, it will take the stored index, at that node. It will take the new index. New index means our current word which we are storing now, and our container vector or container strings. Now it check if the stored index is -1, that means it is a new node, means there is no previous what we call index or answer at this node. So we directly store the new index. But if there is some other word, already present there, then what we do is, then we find the older length then we find the length of the older string which has been stored. Then we find the length of the newer string which we are storing now, right? And then we compare. If a newer length is lesser than older length, then we update our stored index with the new index, right? But what if their length are same? What if both has the same length, newer length and older length are same? Then we check for index. If newer index is lesser than a smaller index, then we give priority to the newer index. So we store our newer index as the best index, so we use this function to update our best index at every node. And here we are comparing first we are comparing the length, and then if they have the same length, then we are comparing the stored indexes, right? We are comparing the not stored indexes, we are comparing which array or which string is appearing first in the what we called string array, right? And we are giving priority to that. So we have seen the update function and how it works, right? So next thing, so whenever we insert a word, what we do is, we update our best index at every node, right? At every node we update our best index as per the new word, that we are inserting, right? Now next we see how we'll build our trie, right? So for every word in the word container, what we'll do is, we'll take the word, then we reverse the word to convert the suffix from suffix to prefix, and then we insert every character and then we check for if we have already a new node. If we have already a node for that character, then we update the best index at that node. If we do not have a node for a character, then we create a new node and again we update the best index for that node. New node, right? So this thing, updating best index, will happen at every node, right? So let's see an example. So suppose if we have in container, if we have these three strings, right? So after reversing, we will get dcba, we will get dcb, and we will get dcbx. So if we see dcb, so all three will share the same path, that is d. So root to d, then to c, then to b, then a, and then x. So up. So if we see at this node, all three will share the same path. So which one should be here, which is the best index here? So if we compare the length is 4, here the length is 3, here the length is 4. So we give priority to the one which has smaller length. So we store the index 1, we store best index here is 1. So here index value is 1. So now when we do a query, and suppose we have to do query for DCB, so DCB we stop here, so we directly see the index value here. So index value is 1, right? Index value is 1, so that is our answer directly, right? We don't have to check all the words, we directly take the best index value stored, right? So for query processing, again we do reverse the query, and then we traverse the try character by character, and we stop when the path breaks, or when we do not get any node, then we stop. And then our last valid node has a index value, right? So we take that index value, and that will be the answer, for our current query, right? For our current query. So in this way we will traverse the queries. So now we'll try to understand, let's see the dry run for query. So suppose if query are cd, then we reverse dc, and then we traverse. So first we go to root, then we check whether we have a node for d. If we have a node for d, then we go to d, else we return, else our last valid node could have been root. Then we go to d, then we see whether d has a child as c. Yes, suppose if d has a child as c, then our query string has been completed. So this is our last valid node. So we check the index value here. Let's suppose index value here is 1, index value here is 1. So for this string, our our answer is index is equal to 1. So 1 is our answer. So this way we will query. So one more thing, our root also stores an index. And why is that? So it may be possible that there is no suffix match. No suffix match means even one single character doesn't match. So in that case the common suffix is an empty string, or right? So in that case the answer should be the globally shortest word. Answer should be globally shortest word. And if there are multiple shortest word, then the answer should be the one which is appearing earlier in the container word, right? So our root node will store, root node stores the globally best index. So if there is a query which doesn't match a single character, in that case the answer will be the index stored at root. So first I have implemented try using pointers, but that has given memory limit exceed to me. So I have to optimize the memory. So now instead of using pointers, earlier I was using pointers, and I got a memory limit exceed, because this new try node, and this happens for every node. So which causes huge memory usage, because here in pointers we dynamically allocate the memory to every node. And the second thing is that pointers are heavy, right? So these things causes memory limit exceed. So then what I have done is, so instead of using pointers, we store the indexes, we store the nodes inside a vector. And now pointers instead of pointers we store indexes, of the nodes, right? So here each child node will store index of the next node, instead of pointer, right? And now see, let's how our current implementation will work. So basically initially we have try is a vector, so we push a new node, in that vector. So our root node will be try of 0, right? Try of 0 is root node. So the next node created will be trie of 1. Then the next node will be created will be trie of 2. So this way the new node, the every new node created will get will get a will get the next index. So suppose if if 10 indexes has already created, so when we create a new node, what we do, we get trie of node dot child of that character, we give 10 to it. That means this new node is pointing to trie of 10, right? This child node is pointing to 10, that means it is pointing to trie of 10. That means the next node will be stored at trie of 10. And then when we traverse and then we get node is equal to trie node dot child of c, node is equal to trie node dot child of c. So we get index from here. So suppose our node is equal to 10, that means our index value is 10. That means now we need to go to trie of 10. The next node is at trie of 10, so we need to go to trie of 10, right? So now if you see, instead of moving using pointers, we are moving through indexes. So this is how we have optimized the memory, because in pointer based approach we are dynamically allocating the memory to the nodes, right? And we are allocating the memory to each node separately. But in case of this index based approach, in this index based approach we are assigning memory to them inside a vector, and as we know, to a vector the memory is assigned contiguously, right? So that's why the memory has been optimized, right? So now we will try to understand the whole approach with the help of an example. Word container has these strings and word query has this string. So first of all, what we do is we reverse our all the container words, because we are converting the problem from suffix to prefix, so that we can use trie data structure, right? So we have reversed all the strings, right? And then we start with initially our node value is equal to 0. So we make trie of 0. Trie of 0 will be our root node, right? So it will store the globally best answer, then next thing what we need to do is we insert dcba. So whose index value is 0. So we go to root node. So at root node till now there is nothing, right? So here index value is equal to -1. So we update this index value to 0, from -1 to 0. Then we check, do we have a child at root for character d? So it will give no, right? So we create a node with so earlier a node value is 0, so we next create a node with 1, right, for child d. So here it will be stored at trie of 1, right? Then we store c, then it will be for trie of 2, right? Then we store b, trie of 3, then we store a, which is trie of 4, right? And here also index value is 0, 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 right? So then we have to, now next thing we need to insert dcb. We need to insert the next word, which is dcb. So we first come at root dcb, then we check index value at root is 0, but the length of this is 4, but our current word length is 3. So we need to update our answer, because 3, this string has lesser length than the stored answer. So we update our answer from 0 to 1, right? So we updated our answer at root from 0 to 1. Then we check, do we have a child at d? Yes, child at d is there. So we go to this node, and then we stored, again we check index is 0. So again due to the length we update this index to 1. Then we go to c, update the index to 1. Then we go to b and again we update the index to 1. So we stored dcb. Now we need to store dcbx, the third word, right? We need to store the third word, which is dcbx, right? dcbx. So we again go to root. Stored answer is 1, length is 3, current word length is 4, so no change, right? So we go to d, then we go to c, then we go to b. None of those nodes index value is changed, so we go to b. There is no child for x, so we create a child for x. So here the index value will be 2, and this is try node of 5, try of 5, right? So this way we have created a try for the all the words, right? This way we have created a try for all the words. So this is our final try. This is our final try node, where root index value is 1. Then for d, index value is again 1. For c, index value is again 1. For b, best answer index is again 1. Then for a, index is 0. Then for x, index is 2. Now we have the query string. Which is, now our query string is equal to, first query string is equal to cd. So we first reverse this, so it will become dc. So we start traversing from the root node. So we first check, do we have a child for dc? Yes, child for d is there. So we go to this node. Then we check, do we have a child for c? Yes, child for c is there, so we go to this node. And now our query string has been completely traversed. So this is our valid node. So what we do, we check the index value stored here. So index value stored here is 1. So for this query the answer is 1. So the next query that we have is x y z. So we reverse, when we reverse we get z y x. So we go to the root node. We check, do we have a child for z? No, there is no child for z, so we stopped here. So this is our valid node for the string zyx. So we check the value stored here, the index value stored here. So the index value is 1. So this is the answer for the string xyz. So this way we'll find the answer for the all the queries. So now we'll see the code part. So in the code part we have taken struct of name node, and we have, each node has an array of size 26 named as child and a index value, and all the childs has value -1 and index value is also -1. Then we have made a vector of type node named as try, right? So this function is basically to update the index value at every node. So what it does is, it takes the stored index value and new index value and the word container. Then if stored index value is -1, that means it is the first word that has been stored to, that has created this node. So we directly update stored index to the new index, right? But if there is already some stored value, then what we do is, then we find the string for that stored index and find its size. So old length will be the length of the older string that has been stored. Then we find the new length of the current index of the current word, and then we compare. If new length is smaller than old length, then we update our stored index to the new index. So this new index will be our answer up to this node, right? Else if both new length and old length are same, then we check if new index is lesser than stored index. Yes, if this condition satisfies, then we again update our stored index to new index. So this function is basically to update the index value at every node, right? So then this is our main function. So in main function we have pushed a node to the try. So this will be our root node, root node having index is equal to 0. That is, it is stored at, our root node is stored at trie of 0, stored at trie of 0, right? And then what we'll do is, then we build our trie. So what it does, we iterate over the all the strings, and then we take the word and then reverse the word, and then our node is equal to 0. That means root node. So we update index for the root node. So we have passed the index value, of the current node, that is our root node, our current index, and our container array, right? And then for the current word, we take the character, then in the current node, we check whether this child is already created. If this child is not created, that is the child value is equal to -1. Means if this child is not created, then we create a new node. So here we are giving trie dot size. Why? Because the new index in the new index of this new node will be the next node. Suppose we have already created 5 nodes, so this will be the 6th node. So we give this node the index 6. That means this child node will point to trie of 6, right? And then we push a new node, in the trie, right? So we have created a new node. Now next thing what we do is, we find the index. So suppose we have created the 6th node, so this node value will be 6. Now we update index for this node. So this is a new node, so its index value will be -1. So that index, so this I will be stored at this index because it is a new node. But if it is not a new node, then we compare the length, and then we compare, if length is same, then we compare the index values of the in the array. So this way we'll build our trie. Then after building the trie, our task is to process the queries. So for queries, we take the string, then we reverse the string, and then we start node is equal to 0 means root node. Then we start from the root node, then we take the character. Now in our current node, we check whether we have a child for this character. If there is no child for this character, we can't move forward, so we break the loop, but if there is a node for this child, then we find the node value, that is trie of node dot child of c. So it will give us the index of the next node. So then what we do is, then we move to the next node, and again traverse until we either our string completely gets traversed, or we do not get a path. So once we traversed the whole string, or we stop at some point, then we get a node, valid node. So what we do is, our answer will be trie of that valid node and the index value stored at that. So we push that index value in the answer array, right? And at the end we return our answer. So I hope I am able to explain you the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.